air over a wing, weather across a continent, blood through an artery, the churning wake behind a car. These all come down to one question: how does the fluid move and what forces does it make? Answer that, and you can design a quieter fan, a safer stent, a faster car, without building a single prototype. Now, physics already gives us the exact rules for all of this. Bundle them together and they're called the Navier-Stokes equations. They govern every flow you just saw. There's just one problem. For almost any real shape, nobody can solve them by hand. There is no clean formula to plug your wing or your artery into. So we don't try to solve them as one giant continuous problem. We do something humbler. We take the whole region of flow and chop it into a grid of tiny boxes, thousands, even millions of them. Because on one box, made small enough, the bookkeeping becomes simple. We only have to track what crosses its faces. We enforce the same law on every single box, step the clock forward, and the computer builds up the whole flow. That's the finite volume method. And our entire story is just what happens on one of these boxes, so let's zoom right into a single one. Here's the plan for this video. We take one tiny cube and we balance whatever crosses its faces, the finite volume method. From that single idea, we derive the law of mass conservation step by step. Start with one cube, sitting still in the flow. The mass inside it is just its density times its volume, and that volume is delta x times delta y times delta z. The box is fixed in space, so the only thing that can change is the density packed inside it. The law we never break: mass is never created or destroyed, so the rate the mass inside builds up equals what flows in across the faces minus what flows out, and since the volume is fixed, that build-up is just the rate of change of density times the volume. How much mass crosses one face each second? Take the density times the speed straight through that face times the face's area. Density times speed times area. Only the part of the velocity pointing through the face carries any mass across it. Look at just the left and right faces, the x direction. Mass comes in the left face at one rate and leaves the right face at another. The net loss in x is the right face flow minus the left face flow, times the face area, delta y, times delta z. Now the one move at the heart of it. Multiply and divide by the width, delta x. That front piece is a difference over a width, the slope of a line through 2 points on the mass flow. Watch as the cube shrinks, the 2 points slide together, the line stops being a chord and becomes the tangent, and the slope settles to one number, the derivative. Nothing was special about x. The very same argument on the front and back faces gives the change in y, and on the top and bottom faces gives the change in z. Before we finish, look at the cube one more time, with all 6 faces in play. Each pair gave us a single derivative. The left and right faces in x, the front and back in y, the top and bottom in z. Add the 3 together, and that's the total mass leaving the cube. By our law, it must equal minus the build-up inside. Put the balance together. The build-up equals minus the sum of those 3. Every term carries the same volume, so divide right through by it. And now the equation holds at every single point in the fluid. There is no box left in it. That sum of 3 derivatives has a name, the divergence. So the whole thing compresses to this: the rate of change of density plus the divergence of the mass flow equals 0. The continuity equation. And for an incompressible fluid, where the density barely changes, it's even cleaner. The divergence of the velocity is 0. So that's the whole move. One tiny cube, mass in minus mass out, is what builds up inside. Shrink the cube, and those differences become derivatives per volume. That gives the continuity equation. And in the next video, we point the very same cube at momentum and derive the momentum equation step by step the exact same way. See you in the next one.